Okay, so these are the different exams. So what I wanted to show you, let's go one by one. Question one. So question one, I asked the following, right? I ask the views in detail, explaining every step with no shortcuts. Excuse me, the multiple expansion of the electric field, right? And illustrate how the dipole and quadrupole fields look like. So, okay, here, many of you did it right. Basically, most of you just copy and paste what I say in my lecture or whatever you Google. It's important that we don't Google. Okay, these questions I want to have them personal and related to the lecture, lecture notes. I want you guys to you can go and say, okay, expansion, multiple expansion of the electric field, and Google this and come with a bunch of equations. But this is not the point I want to make here. I want us to go through the equations. And for instance, there was this question. There are many questions like this, or this question, just checking all the questions, where actually you reproduce very nicely, this point must be said that is far from the source, right? From these sources here, so that we can apply a Taylor expansion later on. If this point where we want to measure the electric potential is if this point is close by to the charge distribution, we cannot apply the expansion, right? So these are the things that we need to say, just not copy and paste, but we must understand why this approach is happening, right? So if we do this, so this is good. We apply Pythagoras. We check the angles. This is 90 minus that. Very well done. But this is what I explain. I don't want you to. I want you to explain this. But when you reach this point, that's good. Please bring R out, and then these guys become this equation, and then this is the equation that we have to substitute. We assume that this is T, as you say here. And now is the point where I want you to do the Taylor expansion because this term T is less than 1. So we can apply the Taylor expansion. This is not said. So we need to learn where our approximations are valid. And in this case, it is valid for a point which is far away from the source. But then from here, and most of you do the same, from here, you just go back to this point, to the final point. This is what I did in class. And I requested explicitly that you go to the potential, go back here and substitute all the 1 plus t to the minus 1 half, all these terms, right? All these terms, to put it back there into the equation and do the calculation yourself and come with the final conclusion, which is this one. But here there's a missing step, which I penalize in the marking. I gave most of it 20 points, but there are 30. But another point I want to make clear is that when here we go. This is very well. These are the equipotential lines, and these are the electric field. So basically, here there's a little bit smaller blobs here, but this is the quadrupole electric field, which is also good. But then at this point, I want you to come and extrapolate and think beyond the box. Otherwise, I explained briefly the other day. Let's go here. So I explained briefly the other day what kind of information. I mean, you have the radiation pointing up and down, right, for a dipole. So what do we, how do we know these things? I mean, once we know these things, you could have said, just for the heck of it and say, wow, I know my stuff. And I would appreciate if you go beyond the question itself and say, look, Prof, look at this. We have this radiation. And we have this radiation going up, and radiation going down. These blobs of for a dipole. Let's say bigger. And now let's see. Here we go. Let's see this tablet here. Let me see. No. So we have all this radiation, and these are the equidistant so basically the radiation goes down here, up there, and down here. These are the lines of the electric field, which go up. And this happens for a dipole, right? For a dipole where in there you have a 1r square and that integration that we have, right? So then for this particular dipole, as you write nicely, implies that what I want to say is that if we have a detector system like we have nowadays, where you place two detectors up and down, right? And you detect this gamma, this is all gamma radiation, right? So if you detect all this gamma radiation in here, right? I'm here. And you have other detectors, which are here, say, and here, where you don't see any radiation, right? The radiation is negligible because most of the radiation goes up and down. So then we can determine experimentally by having this kind of configuration, the nature of the decay, for instance, from 1- to say 0+ state, right? This will be a pure dipole, a pure E1. And this E1 will look like this, right? Emitting radiation, gamma radiation up and down. So these two detectors, this called them gamma ray detectors. The one on top and the one at the bottom will detect more radiation than these ones anywhere else, right? So for the dipole, again, will be something similar, but for the dipole, we'll need those detectors on the sides because these blobs will also emit radiation. And again, for the particular case of the quadrupole, we also get radiation on these detectors on the side, right? So that will tell us that we have a quadrupole radiation. And this will be the example of as I mentioned before, or the other day, 2+ to 0+, where this radiation is emitted in such a way, it's not like this curly arrow, and this will be an E2, right? So this is what I want you to explain and tell me, okay, I've done the calculations. I wanted to know how good you are with the calculations, but at the end, I'm not so sure because the only calculation that I didn't do in class, most of you didn't do it for the test. So this is something that I want you to remember, to notice for the next test, right? So any questions? Where's the chat here? This is as of question 1. Most of you, as I say, did it right, but I don't see the chat now. What is the chat now? Here we go. So I don't see any questions in the chat. So tell me if there's any issues here. Did I make myself clear? Shoki? When I grade you, guys, I want to know the extra 5 points. I want to know that this information which we are providing can be used to determine something, right? Or this is the discussion part that which I want you to come with. That's the missing step. The missing step in equation 1, it was just to substitute this So 1 minus t half, where t half is t is all this thing, right? To substitute this over here, and from here to substitute basically all this binomial expression right here, with knowing that t is equal to this one, right? So that was the missing step, which I didn't do in the class. So now here, point 2. Point 2, I see that many of you made mistakes. This is a particular case where I gave 5 points for each question, which was correct. And this is a 20 points that you are getting almost for free. You know, this cannot have any mistakes. It's just applying basically this 4 plus to 1 plus. Let's see the 4 plus to 1 plus. So the 4 plus to 1 plus it is, many of you did it right, but I don't want anyone to do it wrong. That's what I want to say, because it's easy enough. I just applying certain rules, right? So let's say 4 plus. I think there were enough mistakes to 1 plus. So first thing is, we go and say, okay, this is j initial minus j final, less or equal than the multipolarity lambda, less or equal than j initial plus j final, right? So j initial is 4, j final is 1. So 4 minus 1, 3, less or equal than the multipolarity, less or equal than 4 plus 1, 5. I mean, this is just 1, point 1, point 2. So which ones, with there's a change, no parity change. So then we start with E0, but we know the E0 cannot be emitted by a gamma, because a photon at least need 1 h bar of 1 angular momentum, right? So E0, M1, E2, M3, E4, and so on and so forth, right? So as we know, the Taylor expansion, the first terms are always the strongest ones, right? The E0 is actually the monopole, the charge. And this is 1 over r. The next one is 1 over r squared. The next one is 1 over r cubed, and so on and so forth. So what is the transition? The exciting this 4 plus to the 1 plus. So the minimum is 3. So we start 0, 1, 2, 3. And the maximum is 5. So 4 and 5. So there will be an M5 here, right? So then we say, okay, the minimum is 3. So we start, this is 3. M3 is going to be an M3. And because the magnetic is always weaker than the electric, the next one will also come together, right? The E4. But once we hit the electric, the next one is negligible. The magnetic is much weaker than the electric, so there's no magnetic. So this radiation will look like this. M3, it will be a mixture of radiation and E4, right? So for just one more example, and also where there were some mistakes, the 5 minus to 1 plus. 5 minus to 1 plus. So similarly, in this case, there's a change of parity, 5 minus to 1 plus. In this case, there will be J, it will be 5 minus 1, 4, 5 plus 1, 6, minus lambda, less equal than 6. Let's make 1, and then let's make 2. The possibility starts with parity change, because we have minus and plus. So then we have, starting with M0, the monopole, the magnetic monopole, which no one has seen before. So an E1, M2, an E3, an M4, and E5. So then 4 to 6. So 0, 1, 2, 3, 4. 5, and then the next one will be an M6. Again, it will be the same situation as before. Once we hit the electric, the M4, which is the minimum, it comes with the electric E5, but once we hit the electric E5, the next magnetic is negligible, right? So this will be a M4, and again, an admixture, a mixed transition, E5, right? So these are the things that we need to know. Very simple. There's a parity change, there's no parity change. These are the range of angular momentum that we can have for a gamma radiation. And yeah, okay. That's it. That was very simple. 5 points per transition. Questions here? Correct? Tell me if there's any issues with that one, because that one is very simple, right? Let me stop sharing here because I want you to no question, Prof, from Craig. Okay. Anyone? It seems very easy, but we made mistakes. And for instance, we didn't follow. You know, if the magnetic comes first and the electric comes later, the magnetic it remains, right? Only if you have 4 is magnetic, the magnetic is okay, but then 5 is electric, it's okay, but then 6 is magnetic. Once you hit electric, the next magnetic is negligible, right? Doesn't play any role in the Taylor expansion. All right. Any questions? Asile? Anyone? Ansel? Okay, then now, if there's no further questions regarding this point, let me share screen again. And then let's go to the more, I think here, you see, we get lots of points at the beginning. I gave you 20 points, even if we don't explain things or we don't do a step. I give you 20 points here, and then here comes the issue. The issue is question 3. How will the binding energy curve? And here comes the issue because it's difficult for us to come to a proper discussion, right? So it's difficult for us to come to a discussion because first thing, this is the most difficult part, right? So in every paper, and this is actually a very important point, every paper I write, I spend many hours trying to explain our results, right? Trying to do some calculations, I'm trying to there's a lot of hard work being involved into explaining these kind of questions. How will the binding energy curve change if the range of the nuclear force suddenly changes? So, and we have to come with some kind of conclusions, some kind of logical conclusions. So I gave you some points there, but I'm not really happy with the conclusions that we made here. Here there was some information. There's a lot of some good points here. you know, if the range increases, it will go from 1.5 to 3 Fermi. So hence the nuclear force weakens. So this is a common mistake. Hence the nuclear force weakens. Okay. So if we say that the range of the nuclear force increases, so I don't understand why you are saying that the nuclear force weakens. So say we take our binding energy curve. So, and we discussed and then some of you explain it, that the nuclear, the binding energy curve, because there's a sudden increase around helium-4 and then it starts flattening, right? So basically we assume that the range of the nuclear force, the range of delta, let's call it delta X to be consistent, delta X was approximately the radius of the alpha particle, which was 1.9 Fermi. Let's make it 2 Fermi, right? And this contributed to mainly to the, as we know, the long range of the nuclear force. It was according to the Heisenberg uncertainty principle, it was 1.4, 1.5, but let's say 2 Fermi, basically somewhere here. So if we increase this range to 4 Fermi, that means that this guy, the radius is not going to be the alpha particle, but it's going to keep going up. Again, it's going to keep going up. And we can add proton and neutrons, proton, proton, neutron, neutron, right? But if we add more particles, before nothing happened to those, it's like the binding energy doesn't change. But in this particular case, if we double this, so this will imply that this, obviously we have a different point up there, which maybe well, the radius of the nucleus is 1.2 a to the 1/3, right? So something which is 4 Fermi. So the radius of a nucleus, which is 4 Fermi. So that will be defined as 1.2 a to the 1/3 equal to 4 Fermi, say. So you could determine what this will be the new A here. And this will determine, for instance, where will be the sudden increase here, where the nuclear force doesn't saturate. So from that point we start saturating. So basically that will be a way, one explanation. I'm not asking you to do this in particular. I'm asking you to provide any logical explanation, assuming that the binding energy curve, I mean the range of the nuclear force doubles. So many of you came with this point, with the point of the radius of the nucleus, and there in the radius of the nucleus we assume. Let me see if I open the one. Yeah. In the radius of the nucleus, when we have the radius of the nucleus for the tantalum and the silver, we assume that there was some data points which follow nicely the Rutherford cross-section, this sigma d omega, as a function of kinetic energy in the lab frame. So, but then some of those data points that we have here was very nicely following, and then suddenly it came down there, right? And then we assume that at this particular point, whatever was the energy, let's say 23 MeV, this was in MeV, right? At this particular point, the two nuclei became too close, and so the Rutherford scattering didn't follow anymore, because that's a classical interpretation, but there was assuming 1.5 Fermi there. that at this particular range, the nuclear force play a role, right? And that's why we don't have we have a deviation from this dash line there. So now we assume that in this particular picture, this was R, and R is equal to the radius of the alpha particle, which we know, plus delta X, plus the radius of the, let's say, the tantalum nucleus, right? So then you say that if we increase delta X, then obviously the radius, let's see what happened. Radius of tantalum will be equal to R, which is that distance, determined by equaling the energies, right, in the center of mass frame, R minus R alpha, which was a given, minus delta X. So if this goes up, you are saying that this will come down, right? So this is not a logical explanation. It is not a logical explanation for the following reason. So you have, we are extracting this data from experimental values. So say now we have a new value for delta X, which is double, 2 times delta X of what we have before. This remains the same. This remains the same. So the only thing that will change will be this data point. This data point, instead of coming maybe at 23 MeV, as the nuclei, the nuclear force suddenly starts being active at a longer range. So this alpha particle getting closer at 2 times that range, it will start, so it will need so much energy. It will need so much energy for the nuclear force to start playing a role. But instead of 23, the deviation will happen earlier, right? Maybe, I don't know, I have to calculate by maybe 90 MeV or whatever number, right? It doesn't really matter the number, but the idea, the qualitative idea to say, okay, so now the nuclear force will be, so basically R will be smaller. Actually bigger than before, because that at that particular distance, we have increased delta X. This R will be smaller, I mean bigger, but that R, as we know, is determined from the kinetic energy change. So 1/2 of mu U1 square equal to Z1 Z2 E square 4 pi epsilon naught R, right? Where this E square over 4 pi epsilon naught is equal to 1.44 MeV Fermi. So from here we get R, right? But now we got U1 from the T-lab, right? So this quantity will change now. If we measure this experiment, T-lab will be smaller. And if T-lab is smaller, so R will be bigger, right? If we substitute here R, what is the R is in the denominator here, we move it up there. So the U1 will come down, right? And then R will be bigger. But there won't be any difference in the radius of the tantalum according to this problem. Is that clear? So now we can investigate this further. We can investigate this. There's a lot of information here that we can investigate. For instance, if the nuclear force gets, the range of the nuclear force increases, means that the nuclear force is tightening up the nucleus at a distance, as we mentioned before, which is the range of the nuclear force in this case will be about 4 Fermi, right? Which will equal whatever is the radius, which corresponds to those 4 Fermi. So then the nuclear force, the binding energy will peak later. will peak later, and it will have a much sudden increase in binding energy per nucleon up to that point where you keep adding protons and neutrons in the same way as you add kilos or charges. You know, the more kilos, the more gravitational force you have. So in this case, the more protons and neutrons, the more binding energy, the more nuclear force you will have, because we have increased the range of the nuclear force. And then here there will be a competition with the Coulomb interaction, to the point that we don't know whether phenomena like fission energy, coming from uranium. We explained the other day that you have these neutrons hitting uranium-235, making uranium-236, and then you split the nucleus, because for a very heavy nucleus, the Coulomb force starts, you have a very subtle equilibrium, because the Coulomb force repels. The repulsion is almost at a breaking point, where you just hit it a little bit and then it splits, right? It breaks apart. So now, if the interaction, if the range of the nuclear force has increased, that uranium nucleus is going to be tightened up, right? It's going to be more tight, more bound than before. So is that neutron enough to split so these effects, this will play a role in our creation of energy. It will play a role in the elements that have been produced in our universe. It will play a role in many aspects if we double the strong force, the range of the nuclear force. We make it double, and these are the things that I want you to explore. And this is one of the things that we'll see this Wednesday in the Prac at 2 o'clock. We're going to have an online Prac. It's good that we move online. I will show you this Python code, and we're going to play a little bit and see. I would suggest that we go through the semi-empirical mass formula, also in the Crane's book. Semi-empirical mass formula, also known as the Bethe-Weizsäcker mass formula. And you have different parameters here. This is the volume parameter, the surface parameter. I will explain this on Wednesday, but it will be good for you guys before Wednesday to go through through these equations. So basically, we can show you right now. This is the binding energy curve, and this is the data as taking all the atomic masses as from the 2020. This is atomic mass evaluation. And you can see that with these parameters, the semi-empirical mass formula fits very nicely the red curve, the black curve, sorry, which is the data. These are basically the data points. So then, what happens if we increase the binding energy? We can increase this here and say, okay, let's see what happens if this is the volume term, and the volume term is given by this one here, right? So basically, B over A, the volume term is the dominant term in this mass equation. B over A is, if we increase this, we increase B over A, right? In our binding energy. So remember that this is B over A. So if we increase this volume term from 15.75, which match nicely the binding energy curve. If we do this, Control X, Control S, we close this one and see what happens now. So as you can see, we have double, or more than double, the binding energy per nucleon. You see, this is now, it's telling us more information, because now we can play ourselves with the different parameters and see in a more scientific way how, let me see what it is now, how things change by increasing the binding energy, by increasing the range of the nuclear force. So this I want to explain you this little Python script and the semi-empirical mass formula on Wednesday. We're going to do some calculations for you to keep playing and investigate. So now I stop a little bit, stop sharing, and ask for questions. Songetso, I see you quiet today. What's the matter? As I said before, briefly, it's good that we are doing online lectures. As you know, President yesterday he called a level 2, so we are back to some kind of lockdown. So it's good that we keep. Last week we didn't do any online pracs, any face-to-face pracs, and the same situation will happen for the next weeks. This Wednesday, I want to take the tutorial and do some calculations for you guys regarding the shell model. Tomorrow we start the shell model. So this, what I just mentioned right now, is what I want you to investigate. I want you to explore. You are explorer, right? Being a physicist is something beautiful. You are exploring nature, exploring what is happening if you do this, if you do that. You're asking questions about what if, and then you go and try to understand. There will be a strong force which will be stronger now, and there's a Coulomb force, and the relative, we have to investigate. The atomic bomb, we know, is mostly electric energy. So if fission doesn't play a role, or is difficult to produce because the strong force is stronger, then we have atomic bombs? We'll be able to produce atomic bombs. You will need more energy to split the nucleus, right? And then to produce this as a chain reaction, because remember before, the neutrons themselves, the 3 neutrons that they were broken in the uranium-236, so they're splitting and then producing a chain reaction. So if the nuclear force is stronger, but I want us to explore. Maybe it won't be so easy to have a nuclear bomb. So do you have a feeling of what I want you to do? Chat? Cine? Fulufelo? Anyone wants to win some bonus points for participation? Shoki, do you think we should put this online? I think it's okay. No, I think it's not. For everyone who hasn't come. All right. So the last question. The last question is, what information do you get from the Deuteron? So here I want us. Let me see what you say. Here I want us to. Okay, so everyone can see. Okay. I want you to go to the point. We have information from the Deuteron. We have the and not to come with the stories. What is my probably here? So let me share the screen again. I want us also to be concrete. I ask a question. I don't want you to come with the story of the Deuteron that is called deuterium or whatever. I want us to come to the point. What are the properties of the nuclear force that you deduce from the Deuteron? There are 3, basically. 2 more relevant, or 3. The 3 of them are relevant. 1, the fact that we have a potential, right? And this state here, which is the 1 plus. We know experimentally it's a 1 plus. So J pi is equal to 1 plus. So then from here, we know that total J is equal to L plus minus S, right? Where S is equal to 1/2. So basically you can have up and down proton and neutrons. You can have up and up proton and neutrons because they are different particles. But only if you have proton and proton or neutrons, only the up and down possibility is allowed because of the Pauli principle, right? So then we see, okay, J is equal to 1. So to make J is equal to 1, L can be equal to 0, S is equal to 1, then L is equal to 1, S is equal to 0. Or you can have L is equal to 0 and, 0. L equal to 2 and S is equal to 1, right? So these are the possibilities if you have a J equal to 1. So which one is not possible? So we know because of the parity is equal to -1 to the L, and the parity of this state is positive. So obviously L equal to 1 is not a possibility because that will give us a negative parity, right? So then we agree that L equal to 0, S is equal to 1, and L equal to 2, S is equal to 1. So this comes with two pieces of information. One, that S is equal to 1. So basically the proton and the neutron are coupled, aligned parallel, right, to each other. So which means that the nuclear force is spin dependent. And secondly, we have that L is equal to 0 and L is equal to 2. As we mentioned, this was about 96%, and this was 4%. Some of you explain why there is 96% and 4%, which I appreciate. But basically, L is not a constant, which implies that the nuclear force is not central, right? So this is a very important point and describes the micro world is not a constant, but there's always a probability for something to happen. And then you come here and say, okay, for the 1 plus deuteron, we have a linear combination of states which involve L equals 0 plus L equal 2. And therefore, this is the wave function which will describe the deuteron with alpha squared plus beta squared is equal to 1. And the final thing is that we have reduced V naught, which was about 35 MeV, which is the depth of the potential or the nuclear potential or the nuclear-nuclear interaction to bind the deuteron. And this interaction is actually quite general. This 35 MeV is a quite general depth for a potential. And these are the things that maybe the first two, and the third one is probably not as obvious, and we also deduce it in one of the assignments, right? By solving the deuteron potential. But you know, this is to the point. Don't start calculating the deuteron potential because I just want you to know, to let me know what are the as I say, what kind of information regarding the nuclear force can you extract from the deuteron, right? That was it. Nothing else. This page is playing a little bit briefly. You know, make what I just say, comment it in the exam paper, and you get the 25 points, right? As I say, very important that we go to the point. We don't start telling the story of what happened with the deuteron when the deuteron went to see Winnie the Pooh or whatever happens, right? We focus on the story, we focus on the question, what kind of information can we extract? We know nuclear force is spin dependent. The nuclear force is not a tensor force because L is not constant. And third, also the deuteron tells us The binding energy of the deuteron tells us what kind of potential you need. And if you want, you can explain a little bit of the calculation you did also. I mean, it's fine. You can deduce, but basically, I want the answer to be clear. I don't want the answer to be diffuse in a lot of blah blah blah, right? So to the point. That's it. Any questions, Prof? Did we put both parity and potential strength together 25 marks? Did we put both the parity and potential strength, both the parity and the tensor force, right? And the spin dependence and the potential strength also. Just to add the 25 marks, I'm always very demanding with you guys. I want you to guys, you know, if you tell me just the spin and I always give you 20 marks and the spin dependence and the let me see, when are we getting our marks? Sabelo, good, you're getting your marks whenever I finish marking. So that's also a good question. But as I said at the beginning, to help me marking, the best thing is to have one PDF, because it's difficult to go through. You know, you have 4 questions. I have to go each PDF on the Canva, so it's very difficult to mark everything properly. You know, without. So by tomorrow, actually, by tomorrow, I hope to finish that today, and then by tomorrow I can give you the marks. But basically today we did a kind of a rubric, a kind of a understanding of how I'm going to mark you guys. I'm going to be very demanding, but I'm going to give you marks for doing your work. But it is important, very important, that we learn how to interpret, that we learn how to discuss, how to make conclusions. You know, this happens. I don't care so much about the solution, but about what you think about that solution. Okay, let's see. Any more questions? If not, I will wait a little bit, guys. Please don't be too shy. You know, just ask questions, because there are many things to learn here. As I say, to interpret, we need to read. You know, we need to read. The more, I know we only have 2 weeks, and whatever marks we get for this test, I also want to say one thing. We're going to follow. We have a test this week, Friday. Every Friday we're going to have a test. We have another test next week, Friday. And I want to see an evolution. I know we don't have much time to see an evolution, because in principle, I used to teach the whole semester before. So a whole semester was a better indication for you guys to learn the process and to start thinking on your own, right? To start thinking beyond the box. But as we have the time that we have, we'll see what happens at the end. But I want to see some kind of, I would love to see some kind of evolution, and how these lectures make you think deeper, because this, at the end of the day, is what we are here for, to make discoveries. And to make discoveries and to do physics, you need to be very very sharp, right? And I want you to be and to learn as much as you can, or as much as we can, to be as sharp as possible. So guys, Salman, any questions before we go? Yandisa? Melissa? Ansel, any questions, guys? Vivan, before we go? You need to use these opportunities. So Shoki, tell me what is the situation of the class? How is the class? Are we understanding things? I mean, I know it's very short time, but that's why we need to immerse ourselves as deep as possible in the waters, and that's why I'm saying let's use our waste basket, our bin. This weekend, you know, my bin was full. It's a big bin full of scratch paper, and you know, I am the professor. I used to do this since when I was at the university. I go through the night without noticing, and I opened the curtains. It was daytime, and the bin must always be full. I'm telling you one thing: there's no other way out. Trust me, because I made it, and I know what takes to become a scientist. Okay, a physicist. So it takes your bin, your waste basket to be full every day, and it takes to read and to study a lot. And Google is good as a reference, but you cannot rely on Google to become smarter, to become sharp. You must go Google maybe 1 minute here and see what is the formula. I don't believe it. Remember this formula or whatever, that's important. But to think deeply, forget about Google. It's only you. All right. If there's no more questions, tomorrow we start the share model. I'll bring you the marks. Thank you again for being here, and have a good rest of the day. Remember, the assignment is due tonight.